excuse me, 1 point. All right, so we're picking up today with slides 23 through 39. We've got a bunch of examples to work for you, and also have we're going to start talking about friction and how that affects work and or energy, and we're going to talk about work. Okay? So I'm recording and having a snack. Y'all just going to have to get over it. All right, so here we go. First example, number 8. We have a ball being dropped from here, from this point, down to this point. We don't have to pay any attention to this being y equals 0. What we do need to do is look at a before and an after here. So before, all we have is this ball getting ready to drop, and it's going to drop all the way to here. So this is our delta y, and our delta y is actually 1 meter to here and 0.2 meters here, so 1.2 meters. Please be careful, because what you need to realize is this 1.5 meters is all the way to the ground, okay? And this is 0.5, so this is 1 meter here, and then another 0.2 here. So a total change in 1.2. So before, the only thing we have is gravitational potential energy, which is mg delta y. After, it's all been converted because it's hit this spring and it's compressed our spring. So after it is all converted to u spring, which is 1/2 kx squared. And remember, those are equal. All right. So now we're going to set those equal. We've got m, the mass, which is 2, gravity, which is 10. I don't know what just happened there. A change of 1.2 here, and then we have 1/2 spring constant times 0.2 squared, because remember, this is how much the spring was compressed. All right, so if we do all the math here and we solve, we get a spring constant of 1200 newtons per meter. All right, so now that's the answer to part 1. Checks off. Now it says if the ball has more mass, how would it affect the compression of the spring? Well, in part B, really the way you need to look at this is mg delta y equals 1/2 kx squared. Well, this is not going to change, and that's not going to change. Spring constant won't change, that won't change. So what you're asking is if m goes up, what happens to x? Well, if the sides are proportional, then x is also going to have to go up. Well, if x goes up, that means that the spring is actually compressed more. So we know there is more, and the way we write this is there's more gravitational potential energy to convert to spring potential energy. So the spring compresses more. Now, y'all knew that. Common sense says if you draw something heavier on a spring, of course it's going to squish it down more. But this is the math and the theory behind it. All right. Moving on to the next one. Example 9, energy. Again, we want to start with a before and an after. All right. So what we're looking at is we've got a before, which is we're holding this box in place. This thing is squished down. We're holding it in place, then we're going to release it, and it is going to move upwards like this. So this is my before, and this is my after. My before, if I set this as my 0 line, my before is just spring potential energy. All right? And if I set this right here, what I have afterwards is the box is moving, so I have kinetic energy, 1/2 mv squared. But I also have what? Well, it's moved some distance vertically, hasn't it, right here? So that means I have gravitational potential energy, which is going to be mg times that distance d. We know these are going to be equal because there's not any friction. So we're going to set this up and we're going to solve. All right. So we have 1/2 kx squared equals 1/2 mv squared plus mg times the distance. What we're looking for, just to double check, is we are looking for the final speed of the block when the springs return to its equilibrium position. In other words, it's fully extended, so that's here. We want to know what v is. All right, so let's go through and figure out what we have. If you look, we have 1/2, a spring constant of 955. The distance that it compressed was 4.6 centimeters. Remember, 4.6 centimeters, we're going to multiply that by 1 meter is 100 centimeters. So we're going to divide by 100 and get 0.046 meters. So we get 0.046 here, squared. 1/2, the mass of the block is 1.7 kilograms, times the velocity squared, which we don't know, plus the mass, 1.7 times gravity, times the distance, which is again 0.4046. Okay? So if we plug all of that in and solve for v, we're going to take this stuff, multiply it together, subtract this from it, multiply by 2, divide by 1.7, and we are going to get a velocity of 0.518 meters per second. Okay? All right. Was that all we wanted? And look, checks out. And that's it for that example. All right, moving on to slide number 25. Here we go. This one's not too bad. It says we've got a 4-kilogram bowling ball sitting right here. We're about to drop it from rest, so we know we're starting with no kinetic energy, and it's at the height of 1 meter. There's an unstretched spring below it. That's it at A. So the ball's going to drop, and it wants and then it's going to slowly compress the spring, so it hits the spring at C, and then it compresses it at D, and then finally comes to a rest at E. So what we know is, because it wants the velocity of the ball at position D, we know it is still moving in this direction. So it has velocity. And it's also compressing that spring. So let's do a before and after. This is our before. Our before says we only have gravitational potential energy. Okay? Our after, now here's the cool thing I'm going to do. Yes, this says 1 meter, but I'm not going to pay attention to that. What I'm going to pay attention to is this. It starts here and it ends here. So I'm going to call this my 0 line. So if I call this my 0 line, if this is 1 and this is 0.2, this is really 0.8 from here to here, isn't it? So that is what my distance is that it's actually following. That's my delta y, so to speak, okay? So keep that in mind. We also know the spring is compressing this much, which is 0.2. I know that because it's going from 0.4 to 0.2. So this is my delta x. All right, so let's go back to after. It's moving, so it has kinetic energy, and it's compressing the spring, so it has spring potential energy. So let's fill all these in. So this is mg delta y. This is how it's written on your formula sheet. This is 1/2 mv squared, and this is 1/2 kx squared. And we're just going to take before and set it equal to after. All right, and we'll fill in our numbers. It wants the velocity, so we know we don't have the velocity. So we have mg delta y equals 1/2 mv squared plus 1/2 kx squared. So let's fill in. Mass of the bowling ball is, what, 4? Gravity's 10. It's falling 0.8 meters. 1/2 4 times v squared. 1/2 the spring constant. It told us the spring constant was 490 newtons per meter, and we know it's gone 0.2. So we're going to do 0.2 squared. So we're going to multiply here We're going to multiply this together. We're going to subtract those and then divide by 2. So we're going to get a final velocity of 3.33. And if I'm correct, let's check up here. Yep, look at that. We got it. All right. You can see the before and after. It doesn't matter what it does in between. We just want to know the final state and the initial state. What type of energy does it have and what are we doing? Before, after. Okay. All right, conceptual question here. It says, from the video, explain the energy. Okay, so this is a pole vaulter. Y'all know what a pole vaulter does. He's standing still holding his stick. He's then going to run forward and plant his stick. Dude's going to go this way. Y'all know that. And he's going to fly up over this, come back down the other side, and eventually end up laying on the mat here. Okay? All right, so what's he doing here? If he is standing still and he's on the ground, he's not doing anything. His energy level is 0 here. There's no bar. So now he's running. If he's running, and let's look at these bars, these graphs pretty good. If he is running, the only thing he has is kinetic energy. So let's set this bar at the top, and we will say he only has kinetic, because he hasn't done anything else. All right, so now what's going on? When he hits this guy right here, what he's got is, y'all know how the pole vault works. His stick is going to be springy. So his stick's going to be springy and it's going to shoot him up this way. All right. So if his stick was springy, he had elastic potential energy. Right? And what else? Gravitational, because he's some distance from the ground, isn't he? So now he has gravitational potential energy as well. All right. Now this is the moment before he begins to move. Because if you remember, when he plants his stick, he's almost like he stops. His stick flexes and then it throws him. So this is that moment right before he goes. All right, so now he gets up to the top. And he's up to the top, and what's happened is we've taken some of that elastic potential energy. There's no more potential energy left because his stick is no longer flexed, right? So all we've got is all of this energy being converted into, because he's at the very top of his arc, potential energy. Okay? Now finally, he's here. At this point, he's now splitting it between, he's now moving again, isn't he? He's moving up and down, so we know he's got some potential energy still, but some of it has to have been converted to kinetic energy. Okay? All right, no elastic at that point. Okay, so hopefully you understand how all those worked out. All right, so now we're going to start and bring in work. What is work? Work is the ability to transfer energy. In other words, we're going to take energy and we're going to move it. So if you shove something across the floor, how does it move? Well, you apply a force, don't you? So the force is the vehicle. Okay? You got a force. Now your signs, we're talking about sign conventions for work. The actual formula for work, which is W, work is W, is called FD cosine of theta. Well, theta, that theta is the angle at which, from the horizontal at which you apply the force. So if you're applying your force, if your velocity is moving this way and you apply your force in the same direction, then theta is equal to 0 degrees. And we know the cosine of 0 degrees is 1. That also begs, if you have the velocity, if the object is moving this way, but your force is being applied this way at some angle theta, the only part of it we count is the horizontal component that is working in the same direction. So this is where the F cosine theta comes in. This is the portion of the force here that is being applied horizontally. in the same direction as the velocity. That's all we're worried about, is the part of the force that's in the same direction as the velocity. Okay, which then makes you wonder, well, what happens if I've got something moving this way, but I'm applying the force this way? Well, what angle is it at? It's at a 90-degree angle. So if you were to do FD cosine theta, that would be FD cosine of 90 degrees. And y'all know cosine of 90 degrees is 0. That means this would be 0. So, and think about it, it makes sense. If you push down on something, you're not helping it move sideways. You're simply keeping it, you're simply pushing down. It has nothing to do with moving sideways. So it doesn't really count towards doing work. Only the force that's in the same direction as the object is moving. So I want to amend something. It says if the force acts in the same direction as the object's motion, then the work is positive. That's true. So if the force is this way and the velocity is this way, work is positive. If the force acts in the opposite direction, in other words, if the force is this way, but the velocity is that way, then work is negative. Okay? If the object does not move, 0 work is done. I want to amend that to say, or if the force is 90 degrees to the velocity. Okay? And that's what we just talked about here. That's this case right here. Work is still 0. So there's a couple things you need to look at here. So we have this formula, FD cosine theta. We also need to understand that work is the same as change in energy. But this guy right here is also important. Work is the change in kinetic energy. And you'll see this formula come up time and time again, okay? So you need to know that total work is the change in kinetic energy, but work itself is force times distance times the cosine of the angle of the force being applied with the horizontal. So now it says in which scenario is positive work being done, 0 work being done, negative. So you've got to look at the direction of the force and the direction of the velocity. Well, if the force, this guy is perpendicular to this guy, isn't he? That means the work is 0. In this guy, the force is this way, the velocity is this way, same direction, so my work is positive work. In this case, the force is this way, but the velocity is the opposite direction. This means I have negative work. Okay? Just that simple. And let's check our answers. Yep, we are correct. All right. Is there work in the following situations? A teacher applies a force to a wall and becomes exhausted. So what you have to ask yourself is, does the wall move? If the answer is no, then guess what? No displacement, no D, equals no work. Okay? So if D equals 0, then work, which is FD cosine theta, also equals 0. Okay? A book falls off a table and free falls to the ground. Well, there is a change in distance, and the force is the force of gravity. So there is work being done. There's a force and a change, a displacement. So the answer here is yes, there's work being done. A waiter carries a tray of food above his head with one arm and moves across the room. So we've got this guy holding a tray up. Now he is holding the tray up, straight up, above his head. Sorry. Above his head with one arm. So the force is going this way, but the waiter is moving this way. So what is the work? Well, they're 90 degrees to each other, so the work is 0. A rocket accelerates straight up in the air. So if we have a rocket and it's accelerating, its velocity is this way. Oops, I don't know why I put W. Its velocity is this way, and its thrust is that way. So they're effectively in the same or opposite direction, but it's in line with it, isn't it? So we have work done being here. The work is yes. It's just negative work. Okay? All right. It says, hopefully you understand that. So let's look at a couple of examples here and see what we've got. All right. So example number 11. Now, we're not doing before and after anymore because this is work, not energy. We're simply looking for our formulas. And let's remember what our formulas are. Our formulas are work equals FD cosine theta, and that work total equals the change in kinetic energy. Okay? Well, change in kinetic energy is K final minus K initial. Okay? So work total. That's what it's equal to. So let's do this guy. Part A. It says draw a free body diagram of the example. Hockey player exerts a constant 4.5 Newton force on a hockey puck. Starts from rest and slides across the ice. So we got a hockey puck sliding across the ice. All right, so my free body diagram, if I'm going to look at this, here's my puck. I know I have the force of gravity going down. I have a normal force going up. And I know I have a force being applied to the right. Okay? It could be the left too, I guess. So there's my free body diagram. How much work does the player do on the puck? Well, the player is applying this force F. Well, that's the same direction as the puck is moving, isn't it? The velocity is going that way. That means that the work done is going to be the force he applies over the distance he applies it times the cosine of theta. Well, in this case, since it's the same direction as the velocity and the force are in the same direction, cosine of theta is 0. I mean, theta is 0, so cosine of theta is 1. So the force is what, 4.5? Who moves it 0.15 across the ice, and this is the cosine of 0 degrees. If you plug that in, then you should get 0.675 joules. Okay? Work is joules. All right, so there's B. It says how much work is done by gravity. Well, work done by gravity. If the puck is moving this way, the velocity is moving this way. So the velocity is moving this way, but the force of gravity is moving that way. Look at the angle between them. So work done by gravity would be equal to the force of gravity over the distance times the cosine of theta. Well, theta in this case is going to be 90 degrees, isn't it? So this is going to be force of gravity times d times the cosine of 90. Well, the cosine of 90 degrees is 0. So the work done by gravity is 0. All right? You can just know that because you know that gravity is going straight down, but the velocity is going to the side. So it's 90-degree angle. Work is 0, remember? How much work is done by the normal force? Well, if gravity is at 90 degrees, then so is the normal force. So we can assume the work here is also equal to 0. Now, if it was on an incline, that would be different. All right, so now E. It says, what is the change in the puck's kinetic energy? So delta K. Well, the change in the puck's kinetic energy, if you remember, delta K is equal to the total work done. Well, the total work done, as far as I can tell, the only work that's being done, that would be work due to gravity plus work due to the normal force plus the work due by the player, right? Well, that's 0, and that's 0, and this is 0.675. So the change in kinetic energy is 0.675 joules, all right? In there. Sailor uses rope. Uh-oh, now we're at an angle. Now we have this angle right here, which is our theta, okay? So now we've got to look at this. He's using a rope. By the way, this should say an initial velocity of 2 meters per second, just so we know. I don't know why I got cut off. All right, so we've got a sailor. He's using a rope, and he's pulling this way. So this is where the direction my force is going. 40 kilogram boat. So this guy's 40 kilograms. And it's moving a distance of 30 meters along the dock. So the distance D is 30 meters. Okay. So how much work does the sailor do on the boat if he exerts a force of 255 newtons? So work done by the sailor is going to be the force that's applied, distance times the cosine of the angle. All right. So that would be 255 newtons over 30 meters at an angle of 25 degrees. So cosine 25. Okay. That makes it 6,933.25 joules. All right, so B, what's the total work done on the boat? Well, if we were to think about a free body diagram here, shows that you've got a force going this way, you've got the force of gravity going this way, and that's really it. You probably have a buoyant force going the other way. But both of these, the boat is moving, velocity-wise, the boat's moving that way. So force of gravity doesn't apply, neither does the buoyant force towards work. So the work here is only going to be equal to the component of this force in the same direction as the velocity. And since this is theta, this is going to be F cosine of theta. Now you see where that goes. So work total is just going to be the work done, excuse me. We've already figured out what the work is from that. It's the work done by the sailor. So it is 6,933.25 joules. All right, so now let's look at C. It says, what's the speed of the boat? Well, if we know the total work, we know that's the change in kinetic energy. Well, we know that's K final minus K initial, don't we? Well, that would be 1/2 mv final squared minus 1/2 mv initial squared. And we know W total because we just found that. 6,933.25 joules. So let's plug the rest of this in. 6,933.25. 1/2 the mass of the boat. And if I remember correctly, the boat is, what, 40 kilograms? Let's look. Yep, 40 kilograms. 40 times V final squared minus 1/2 40, and it said initially it was going 2 meters per second squared. So we're going to take and work our magic with our math, and we get a final velocity of, what, 18.73 meters per second, okay? And sure enough, you can't really tell, but that's that's there, okay? Hopefully you're getting this. So now we've got a buoy exerting a force at a 29 degree above the horizontal. So if we're going to draw our picture, we've got a sled, and we've got a force that's going like this, and this is 29 degrees. This is my force being exerted, okay? And the sled is 6.4 kilograms. All right, it says find the work done by the buoy if the sled moves 2 meters, assuming the sled starts with an initial speed and slides horizontally without friction. That's a good thing. All right, so let's see if we can figure this out. In part A, we want to know the work done by the buoy. That's going to be the force times the distance times the cosine of the angle. So let's figure out what that is. The force was 11 newtons over a distance of 2 meters times the cosine of the angle is 29 degrees. So that is 19.2 joules, okay? Now, B, if a frictional force is 2 newtons, what's the work done by the frictional force? All right, so let's go back to our let's go back and actually look at a free body diagram here. This always helps. You've got the sled. You've got this force going at an angle here. You've also got the force of gravity. You have the normal force. And now it says we've got a friction. Well, if the sled is moving in this direction, force of friction is this way, isn't it? Okay, so it's going to be, the cosine here is not 29 degrees. This is 29 degrees. From here to here is 180 degrees, isn't it? So what we need to find out is the work due to friction is FD cosine of theta. Only this is going to be the force of friction, which was 2, over the, what, 2 meters it moves, times the cosine of 180 degrees. Now you don't have to do this cosine of 180 thing. You can just reason it out in your head that friction is going to take away. It's going to be negative work because it's going in the opposite direction of the velocity, right? So you don't have to do the cosine. You don't even have to do the cosine of anything here if you don't want to. But it will work out if you do it that way. What we do know is it ends up as negative 4 joules. Okay? So however you want to make it work, you can either write the cosine of 180 degrees in, or you can leave it off and just reason through that if friction is going that way, if the force is going that way and the velocity is going this way, that the work is negative, right? Which we found it was. So then it says work total. Work total is going to be the work done by the boy plus the work done by friction plus the work done by the normal force plus the work done by gravity. Well, these are both 0 because they're both perpendicular. We found the work done by the boy was 19.2, and we found the work done by friction was negative 4. So we end up with 15.2 joules of work total. Okay? 6 more slides to go. Example 14, but they are getting more complicated. It says a rider pushes a bike up a hill that has a mass of 1.3 kilograms. So my bike is 1.3 kilograms here. And it's a steep hill. We've got a 25-degree incline. And the road itself is 275 meters. So that's the distance, D. So my distance, D, is 275 meters. My mass is 1.3 kilograms. All right, my theta is not 25 degrees in my formula. We are actually going to call this phi. Okay. Phi is 25 degrees. Theta, believe it or not, theta is going to be, we're going to have to do our free body diagram to figure out what theta is going to be. So let's do free body diagram first. Okay. So here's my free body diagram for this guy. I got a bike here. We're looking at the bike. We know the force of gravity is straight down. But the normal force is this way. We know the bike is being pushed up the hill, right? So there's a force going this way that he's applying. But we also know that there is a frictional force at work here. Okay? Oh no, it says neglect friction. So we don't even have to worry about friction. Isn't that nice? So we don't even have to worry about that. All right, so now the next thing we have to do is think about the fact that this force of gravity is split into 2 chunks, isn't it? You thought this was going to go away. It is not. This is theta right here, okay? Or phi, excuse me. Gonna end up confusing y'all, and I don't want to do that. 25-degree incline here means this is 25 degrees. Let's just do 25 degrees. So now we know that this is force of gravity times the cosine of 25 degrees. And this guy right here is force of gravity times the sine of 25 degrees. Y'all are used to this. All right, so let's talk about all the things that we've got going on here. Well, this chunk of gravity, let me highlight here. This chunk right here and this chunk right here are the only things that are going to contribute to the work. They're the only things that are going in the, why do I say that? Because what direction is the bike moving? The velocity is moving up the incline. So they're the only things that are going in the same direction as the velocity, or the opposite direction of velocity, okay? All right, so it says how much work is done by the normal force? Well, the normal force is perpendicular to the velocity, isn't it? So that is 0. How much work is done by gravity? Well, there is a portion of gravity that actually does go in the same direction. It's negative though, because it's going backwards. This one's going backwards this way, and the velocity is going forward, so the work is negative. And it's going to be mg sine of 25 degrees. So that means it's negative the mass, which is 1.3, times 10, times the sine of 25 degrees, okay, times d, the distance it's going up the hill. So this would be times 275 meters. That ends up being negative 1,510.86 joules, okay? So this is part B. Now part C says how much work is done by the rider. Well, the work done by the rider is simply the force. So the work done by the rider is this right here. So there's my work there. That's going to cause the work done by the rider, right? And it's in the same direction as the velocity, which means so my work is positive. So it's going to be force times distance. Now, why am I not putting cosine in either one of these, cosine of theta? Because it's in the same direction. It's either 180 degrees or it's 0 degrees. So cosine goes to 1. So if we take and we plug this in, we get the force, which was 25 newtons times 275 meters, gives us what? 6,875 joules, okay? So now it asks, what's the total work? So D, work total is going to be the work done by gravity plus the work done by the normal force plus the work done by the rider. Well, the work done by normal force is 0. The work done by gravity we found was negative 1,510.86. Work done by the rider is positive 6,875. So we just subtract those and we get 5,364.14 joules. All right. So now, part E asks us what's the final speed? Well, in E, we know that work total is equal to change in kinetic energy. So that's equal to K final minus K initial. All right, assuming that K initial is 0, because we're starting from rest, okay? So if we assume K initial is 0, then what do we get? We can set this equal. 5,364.14 equals 1/2 mv final squared. So 5,364.14 equals 1/2 the mass of the bike, and the mass of the bike was what? I can't remember. Mass of the bike was 1.3 kilograms. 1.3 times the velocity final squared. So velocity final is, ooh, he's humming, 90.85 meters per second. I'm not sure I'd want to be on that bike at the bottom of the hill. Okay, so now finally E, it says, that was E. F, if the incline was steeper, would this require the rider to do more work or less work? Guys, instinctively you know it's more work, but you got to be able to justify it. So F, we're going to say it's going to require more work. But now let's figure out why. Remember what we figured out. We figured out the only thing we had here was gravity and the rider. Well, the rider doesn't have an angle, but that gravity does. So work total, work due to gravity and the work of the rider, well, that doesn't change any. That's not going to change any. But what will change is the angles getting steeper. So let's plug these all in. So what we got was work due to gravity. If you looked up here, work due to gravity had the angle in it of the hill. So it would be negative mgd sine of theta. And I want you to think about what theta does. So this is gravity. This work of the rider is just, what, FD? So that's not affected by the hill getting steeper. Well, as theta goes up, sine of theta also goes up. If the sine of the angle goes up, then this part right here gets bigger. So the work due to gravity gets more negative. Well, if the work due to gravity gets more negative, then it's going to require more force from the rider, isn't it? To balance it out, to keep the same total work, right? All right. More work. So instinctively you know the right answer, but you got to be able to prove it mathematically. All right, so work, energy, and calories. We're going to get started on this, but we're not going to probably get into the calories yet. We're just going to talk about work energy. All right, so work example number 15. This is the same deal all over again. What we have right here is we've got a kid going down a slide. He's going 5 meters down the slide. So this is 5 meters, okay? He's got a height of 2.5 meters and he ends up down here at the ground, which is 0. All right, what we do know is this is a right triangle. What we don't know and what they haven't given us is what that angle is right there. So guess what we have to do? The first thing we've got to figure out is what is that angle. All right, so let's figure out what that angle is. So if we draw a right triangle up here, and this is theta up here, and we know this is 2.5 and this is 5. Well, this is adjacent and this is hypotenuse, so that's cosine. So the cosine of the angle is equal to 2.5 over 5. So theta is going to be the inverse cosine. 2.5 divided by 5 is 1/2. Well, I know the inverse cosine of 1/2 is going to be 60 degrees. You could check that with your calculator if you wanted. So this is a 60-degree angle up here. So if this is 60 degrees up here, then this is also 30 degrees down here. So it just depends on which one you want to use. So it says, how much work does gravity do on the person? So to figure this out, we need to do a free body diagram. Okay? So we've got the dude sitting here on the slide. Force of gravity is down. Normal force is this way, right? Okay, he is sliding down to the bottom of the slide, isn't he? Okay, and what did we want? How much work does gravity do? Oh, well, that's the only thing that's happening here. He's not sliding. Nobody pushed him. He's just sliding, okay? So right now, this is what our free body diagram looks like. So what we can do is we can figure out, and he's sliding this direction, isn't he? So we've got to break this into its components. Well, all right. So if we break this into its components, however we want to do it, and I don't like the way that looks. I think the way I would like to draw it is I would like to draw it, well, we could. We could draw it this way. That would be easier. And this, guys, is going to be 30 degrees. You know how I know it's 30 degrees? Because I said that down there at the bottom here was 30 degrees. And remember, if we do this way, this angle is always the same as this angle. All right, so we got 30 degrees here. So the force of gravity, in other words, just this chunk right here is going in the same direction as my velocity. which means that when I do the work due to gravity, I'm going to take that force of gravity right here, and that would be sine theta times the distance he's traveling, right? All right, so this is mg d sine theta, which means that it is mass of the person. Mass of the person is 75 kilograms, g is 10, distance is 5, and this is the sine of 30 degrees. You end up with 1,875 joules when you throw that in your calculator. Make sure you're in degree mode. So that was A. Now B says, what's the speed of the person at the bottom of the slide? Well, guys, I'm going to do this as an energy thing. Why would I do it any other way? Because at the top here, I got a before, and at the bottom here, I have an after, don't I? So for part B, the before is just gravitational potential energy, mgh, or mg delta y if we want to use what's on our sheet. After is simply kinetic energy, which is 1/2 mv squared. Okay, so let's set these equal. Mg delta y equals 1/2 mv squared. Masses go away, right? So we're left with 10. He changes 2.5 meters is 1/2 v squared. So we're going to take v and we're going to solve for v. So v is equal to the square root of 50, which is about 7.07 meters per second. Okay, so there's part B. Part C says if there's a frictional force, what's the work done by the frictional force, and then what's the total work? Okay, so that's going to change our picture a little bit. Frictional force, we've now got a frictional force going this way. So if we've got a frictional force going that direction, now we have negative work being done by friction. Negative force of friction times the distance, right? Because it's going in the opposite direction of velocity. Force of friction is going backwards, velocity is going forwards, so therefore the work is negative. So now let's figure out what the force of friction is. Well, we know the force of friction, they told us, is 12. It says 12 newtons. Times the distance down the slide, which is 5, means this is negative 60 joules. And now it says find the total work. So work total is going to be the work done by friction, work done by the normal force, work done by gravity. Well, normal force is 0. Work done by friction is negative 60. Work done by gravity, we said, was 1875. So we have a total work of 1,825 joules. Okay? All right, closing in. 37, conceptual question. It says, look at the following diagram. You have two scenarios. You are going to put a box in this truck. You can either lift it straight up and put it in the box, or you can slide it up the ramp and get it in the box. It says, which scenario does the person do less work? Is it scenario 1 where you lift straight up, scenario 2 where you shove up the ramp, or scenario 3 where they're both the same, or it's impossible to know? Well, what is work? Work is the force you exert over distance, correct? Okay, times the cosine of the angle. Here's the thing. In both of these cases, this distance right here, regardless of the angle, that distance is the same. D is the same for both, and force is the same for both, then the work in scenario 1 is the same as work in scenario 2. So the answer is both do the same amount of work. Now, why doesn't it seem like it? If they're both the same amount of work, why would we use a ramp? Why is it easier with a ramp? Well, it doesn't have anything to do with the amount of work you're doing. What it has to do with spreading it over a longer period of time. It takes you longer to push it up there so it takes less power. It doesn't take less work. It's the same amount of work. It just is less power, which means that because it takes longer to shove it up, you're slowly doing the work over time versus really fast having to shove it up. Any of you who've ever done any powerlifting, you know that if you have to lift quickly, it takes more work to snatch something up than it does to slowly lift something up. All right. Example 16, 2 slides to go here. Example 16, we've got a 1,620 kilogram car coasting 25 meters down a hill at an angle of 6 degrees. Total work done is, oh, and by the way, this should read 10 to the 4th power. So 3.75 times 10 to the 4th joules. Find the magnitude of the force of friction. So first thing it says is draw the free body diagram of the car. So let's go over here, down here, and draw our free body diagram. We've got a car right here. It's going down a hill. So we know we've got the force of gravity going this way. We've got a normal force going this way. And it says there's a frictional force, so we've got a frictional force going this way. Okay? There's our free body diagram. Boom. We're good. All right. Find the magnitude of the force of friction. So in B, the magnitude of the force of friction. Well, how do we do that? What do we know? Well, we don't know the coefficient of friction, which is a bad thing, because C, it's actually asking us for the coefficient of friction. So we can't do it the way we would normally do it with Newton, which is to take the force of friction is equal to the mu times the normal force. So how else can we figure it out? Well, we can figure it out through work, guys. We know, and they've given us this hint, because they gave us the total work done. We know the work done total is going to be the work done by the normal force plus the work done by friction plus the work done by gravity. Well, the work done by the normal force is 0. So now all we have to do is figure out what the work is done. We know the total work, 3.75 times 10 to the 4th. We don't know the work due to friction, but we can find that. Sorry. But we can find the work done by gravity, because this is going to be the force of gravity times what? The distance it goes down. So let's break this up. Force of gravity we need to break up right here into its component pieces. This is 6 degrees. I believe it said it was 6 degrees. Yep. So this is 6 degrees up here. So now this piece, which is the part we weren't interested in, is mg sine of 6 degrees. So that's where we're going to get this from. So 3.75 times 10 to the 4th is the work due to friction plus mg d sine of 6 degrees. So let's plug in. Work due to friction is the force of friction times the distance. Well, the distance down the ramp is what? Distance down the ramp is 25 meters. So this is 25 meters. The mass of the car, if I remember correctly, I don't remember, the mass of the car is 1620. So this is 7,620 kilograms times 10. Distance is 25 meters times the sine of 6 degrees. You get through all this in your calculator and do your work, and the force of friction, which is what they were asking you for, is going to be equal to what? It's actually going to be equal to negative 193.36 newtons. Here's the problem though, it said magnitude, right? Magnitude of the force of friction, which means we need to take the absolute value. So the magnitude of the force of friction is equal to positive 193.36 newtons. Okay? All right. So now, how can we use that to find the coefficient of friction? Well, if you look in part C, we know that the force of friction is equal to the normal force times the coefficient of kinetic friction because it's sliding down the hill. So this is what we're looking for. So we know the force of friction. We don't know the normal force, but we can find the normal force. Normal force here, right here, is equal to this chunk of gravity. Well, that chunk of gravity is mg, cosine of 6 degrees, isn't it? So these two guys are equal. So force of friction is equal to the normal force, which is mg cosine of 6 degrees times mu sub k. Well, I know the force of friction right here, 193.36. I know the mass is 1620, gravity is 10. This is the cosine of 6 degrees times mu sub k. All I have to do is do some dividing, and I get mu sub k. Coefficient of kinetic friction is 0.012, and it's unitless, remember? All right, is that it for that one? Yep, what's the coefficient of friction? All right. That's going to help us solve our problem, isn't it? Last example. Car of mass m coasts down a hill at an incline. This, by the way, I don't even know what this is. We're going to get rid of that. That doesn't have anything to do with anything. Angle of the horizontal. Find the total work done on the car as it travels the distance. All right, fine. Let's do a free body diagram so we know what we're dealing with here. Car in an incline. So we've got force of gravity. We've got normal force. Include the force of friction. So force of friction, it's not being pushed, it's coasting. So that's it. That's all we have. So we know that work total has to equal the work done by friction plus the work done by the normal force plus the work done by gravity. Well, we know the work done by the normal force is 0 since the car is going this way, right? So now let's figure out if we can figure out what the work done due to friction is. It's going to be the force of friction times the distance. But it's opposite the velocity, so we know it's negative. Work due to gravity. Well, we're going to break this into its component pieces. We know this is theta. So this is mg sine of theta down here, right? And why am I interested in this particular chunk of it? Because this chunk is the only chunk that's going in the same direction as velocity. So we know that the work due to gravity is going to be the force of gravity times that same distance. Okay. So negative force of friction. Force of friction is what? Mu static, since it's rolling, not sliding, times the normal force, times the distance, plus mg sine theta times d. All right, normal force here is my normal force. Well, it's equal to that chunk right there, and that chunk right there is mg cosine theta. So I can plug that in. My total work is equal to negative mu sub s. Normal force is mg cosine of theta times d plus mg sine of theta times d. So let's just pull out what we can that's the same. I know I can pull out, I've got an m that's the same, a g that's the same, and a d that's the same in both of these. So I'm going to factor that out to the front. So this is negative, or this is mgd, and we can flip these order around because we get a negative in front. So this is positive mgd, and this would, we're going to make this sine of theta minus mu sub s cosine of theta. And that is the total work. And that's the only way you have to do it. All right, guys, that's through slide 39. When we get to work, when we get to class next time on Monday, you'll be expected to do homework number 2. All right. And then we'll have a short, potentially have a short little, we'll have some question and answer on the previous homework, and then you'll jump in to this. Okay. That's all I got for you for now.